So this is going to be a quick video for the solution to this problem, which is a situation where we have this beam and we're trying to set up conditions for static equilibrium and then ultimately determine what the forces are acting on the beam. So the first thing that we want to do for a problem like this is to draw a Freebody diagram for the situation. So we're going to have, here's our beam of mass capital M, and this has several forces acting on it. This is the tension that the mass hanging right here is acting on it. There is the tension in the string connected to the wall. There is the normal force, or the force from the wall that is acting in the y direction. The normal force would really be more than the one in the x. But this is what I called, let's see, T wall and P. It's in the pin, so it's a P sub x and a P sub y. So this is going to be P sub y. This is going to be P sub x. P sub x, okay? And then we also have the force of gravity acting at the center. Now we also want to put here some coordinate systems, so when we're summing our forces, we know what the positive direction is going to be in x and y. Okay, so then the other mass that we have here is going to have this tension T sub lowercase m going up, and then mg going down. Okay, so then once we have that, we want to write a system of equations by applying Newton's second laws and the condition for static equilibrium. So this is part A, this is part B. So for part B, we say the sum of the forces is equal to mass times acceleration in general, but because we're considering static equilibrium, nothing's going to accelerate, so this is going to be equal to 0. So then we have the same, or something very similar, when we say sum of torques. This is going to be equal to I times alpha, which is also equal to 0. So let's first look at the simpler of the two of these. This is going to be the mass m right here. And so I'm going to define the positive y direction for this one to look like this, so that when I sum my forces in y, this is going to be equal to T sub m minus mg equals 0. This says that T sub m is going to be equal to mg. So then we can do the same thing for capital M. We can sum our forces in the y direction. Sum forces in y. This is going to be equal to, because this angle here is theta, there's the angle theta right there. This is going to be T sub w times sine of theta plus P sub y minus capital Mg minus T sub m. And those are all the forces acting in the y direction. Let me make that subscript for that m a little bit closer here. So this is going to be T sub m. That's equal to 0. Okay. Then we can sum our forces in the x direction. So sum of forces in the x direction says that this is going to be equal to P sub x minus T sub w cosine of theta, which is equal to 0. And the last thing we need to do is sum our torques. So when we're summing our torques, we need to pick a point that we're going to sum the torques about. And the most convenient choice for a point to sum the torques about is a point where multiple forces are acting, because torque is going to be equal to R cross F, which is going to be equal to R times F times sine of theta times n hat. These are both magnitudes. So when we look at this, if the distance to the force is 0, then the torque is 0. And so we choose this point, we choose the pin to be our point of rotation, then there's no torque from Px and Py. It makes our equations simpler that way. So doing that, and then defining the clockwise direction to be negative and the counterclockwise direction to be positive, we can say that the torques acting on this, we have mg, capital Mg, acting a distance of L over 2 from that point of rotation. So this is L over 2 times mg. The angle in between this force and the vector that points from the point of rotation to where the force is acting is 90 degrees. And so when we're looking at the sine of theta, that's going to be sine of 90, which is 1. And this is also going to be negative per our convention here for clockwise being negative. The next one that we see when we're walking along here is going to be the torque created by the tension. And this is going to be some distance 3/4 L. So this is going to be 3/4 L times the force, which is going to be TW, times the angle in between R and r and f. In this case, it is theta. But we know that times sine of that angle, that is. So this is going to be w times the sine of the angle in between, which is going to be theta. Now, another way that you can look at this is you can say, I want the component of this force that is perpendicular to the vector that points from the point of rotation here. And by looking at this, that component is, TW sine of theta. Okay, so that's another way, and it's an analogous way to see that what we really want is the TW sine of theta. Okay, so now that we have that, we can put in the correct sign for the direction this is going to rotate. This is going to cause us to go in the clockwise direction. This is going to be a plus. Okay, so then the last torque that we're going to have is going to be from this T sub m. This is going to be acting a distance that's the whole length here. So this is going to be L times T sub m. This is 90 degrees right here, and so it's going to be the sine of 90, which is 1. And then negative, because this is causing a rotation in the in the clockwise direction. Okay, so then this is equal to 0. So there are our equations that we have. Now, the next thing that we can do is we can determine what these are. So we can find p sub x, p sub y, t sub w, and t sub m. Okay, so we have t sub m already, actually. So we have this. So let's summarize what we have for our equations here. And I'm going to rearrange them a little bit to make it a little bit easier to see. So what we have is TW sine of theta plus p sub y is equal to capital MG plus, we know that t sub m is going to be lowercase mg, so this is going to become a lowercase mg. The next equation says that p sub x is going to be equal to TW cosine of theta. And the last equation is going to say 3 over 4 L TW sine of theta is going to be equal to L T sub m, which is going to be mg, plus L over 2 times capital MG. Okay, let's get rid of this little dot that I have here. Okay, so now when we're looking at this, something that's good to do, and I took a first step here for algebraic with solving this, and it was getting rid of the negative signs by moving things to the opposite side of the equation. But something that's good to do is to think about what are the things that I know here, and what are the things I don't know, and what is it that I'm solving for. So the things I'm trying to solve for are t sub w, p sub x, p sub y, and that's it, because we've already found t sub m. Okay. So if we look at these equations, the way I have these written, you can look at them and say, okay, well, this first equation has 2 of those things. The second equation has two of those things. The third equation has 1 of those things. So we can go to the third equation first and solve for this one more easily because it's not coupled to any of the other variables. So that's where we're going to start. So looking at this, first thing we can do is we can get rid of these L's. And I'm also going to factor out a G from this. Okay, so we're going to have G on the outside. Okay, so then what we can do is we can divide this by 3/4 sine of theta, or analogously multiply this by 4/3 times 1 over sine of theta to get this t sub w by itself. So this says then that t sub w is going to be equal to 4/3 times m plus capital M divided by 2 divided by sine of theta times g. And looking at this now, this is written completely in terms of things that we know. Okay. Now, the next thing that we can do, now that we have this, we can take this and plug it into the second equation. So when we plug it into the second equation, we end up finding that p sub x is going to be equal to 4/3 times capital M plus, lowercase m plus capital M divided by 2 times, I'm going to erase this and write it again because it's a little sloppy. So this is going to be times m plus capital M divided by 2 times G times the cotangent of theta. Okay, so where am I getting this cotangent? Well, when I take this and I plug this in here, I end up having a cosine of theta divided by a sine of theta, which is equal to a cotangent of theta. Okay, so that's that one. So I have p sub x. The last one that we need is p sub y. So p sub y, we can rearrange this so p sub y is by itself, is going to be equal to capital M plus lowercase m times g minus t times sine of theta. This is t sub w. And then we can just take t sub w and plug it in here. So this is going to say that p sub y is going to be equal to capital M plus lowercase m times g minus 4/3 times capital M plus, or sorry, lowercase m plus capital M divided by 2 times g. And the sine of theta here that I have here cancels the one that I have there. And that's the last one. So that's it. All of these problems are really the same. It's just a matter of drawing a free body diagram, writing the equations for your free body diagram, and then there's some algebra that you have to do afterwards. But the most important part for any of these problems is in what I have here for A and B, is setting up the free body diagram and then writing the equations from it. Everything else from there is, it's, as people say, just algebra. Okay, so that's it for this video. Take it easy, guys.